Good afternoon, everyone. My voice is audible for everyone. If it is
Yes, it
audible,
is audible.
okay,
Yes, it
okay,
is
okay.
audible.
Thank you, sir. Okay. Today's session we'll see on signal processing and communication. During session, please keep mute your mic. Otherwise, noise will come. If you have any query or questions, you can write in the chat box. I will answer after the session, or if I have time, then during the session also I will answer that questions. Okay. About myself, Akhilesh Kumar, Assistant Manager, Application Engineer for MathWorks Products in Design Tech System Limited, and Mr. M. Jaffer, he is a National Manager for MathWorks Products in Design Tech System Limited. So he is helping and coordinating to provide such kind of webinars. So this is our agenda for signal processing, which we are going to see here. I prepared demos and examples based on the agenda which I shared. So in signal processing, the things which we are going to see: introduction to signal processing toolbox, which is available in MATLAB, plus how to generate signals, how to measure signals, how to filter signals, means when to apply IIR filter, when we are going to apply FIR filter. Also we are going to compare cost of that also. And further summary about communication, which we are going to see, that is introduction to advanced communication system, general QM modulation using in AWGN channel. So here we will see how to calculate the bar also. One demo we will see on live audio modulation. So using Simulink, how to modulate and demodulate and transmit on the channel live audio. We are going to see differential binary phase shift keying modulation and demodulation using relay, as well as we will use AWGN channel also in this case. So in this case we will calculate BE bar as well as that is a symbolic error rate and bit error rate. Both we are going to compare in that case. So two ways we will compare in this: the theoretical performance, the theoretical bar, or for and experimental, means the bar which we got from after modulation and demodulation. Okay. Further we are going to say visualize antenna coverage map and communication link. So that is a very important and special today here, that physically we are not able to install the antenna, right? If you have to I have to select the multiple places, and it will be very costly that physically I am going to install antenna and all these things. So virtually on the map, how we can do this kind of things, like if I have to measure the coverage of that, what is the distance between two antenna, what is the angle between two antenna, this kind of things virtually on the map, how we can do. Either we are using massive MIMO, or we are using 4G or technology in that case. Okay. And further more toolboxes we will see, communication related toolboxes what are available in MATLAB. Okay. So first of all we will start from introduction to signal processing. See, sensors are everywhere. First of all, why actually we require signal processing? That is a big question here, that why we require a signal processing. So as we see that because of IoT, sensors are everywhere. So whatever data you are logging from the sensor, there can be different kind of noise, there can be spikes, there can be outliers, or maybe that will be a trending kind of data. So we require to remove that noise, outliers, especially signal processing we study to remove the noise from the signal. So that's why we require a signal processing. Either you are using communication, you are transmitting signal from one end to other end, then noises are introduced, right? So we require to study the signal processing to remove that noise at the receiver end, right? That is very important. So sensors can be anything. It can be your healthcare devices, or it can be sensors are available in your smart mobiles also. Nowadays sensors are available in vehicles also. It can be mobile communication sensors, right? Communication 4G, 5G, right? Signals are everywhere which we see. And why analyze signal using MATLAB? MATLAB makes signal analysis tasks very easy. Why? Because it is a high level language. If I am talking about high level language with MATLAB, means the mathematical equation which you write in your notebook as it is, you have to write in a MATLAB. So you don't have to remember actually that what functions are available there. Two things you require in MATLAB: either you are working on signal or communication or other applications if you are using with MATLAB, that how to get help in MATLAB and what you can do using MATLAB. These two things are very important if you are using MATLAB. There is an interactive development environment. Let's say if you are getting any error on any line, proper output you will get from MATLAB that in this line this is the error, please replace it, or your matrix dimension is mismatched, depends that what kind of errors are there. MATLAB will let you know. Apart from that, if you don't want to write code, we have apps also. Like I will show you BERT tool, that how you can calculate the bit error rate using apps without writing a single code for that. Easily share your analysis with others, so lots of options are there. Whatever algorithm you develop in MATLAB, you can share it as a PDF file, as a doc file, as HTML, or in latex form. Apart from that, if you want to interface with other languages, so you can generate libraries for Java, for C, C++, you can interface with .NET, .com. There is a MATLAB compiler SDK to generate libraries for other languages. Else you can use MATLAB compiler to generate a .exe file. You can generate standalone applications for Mac. You can generate standalone applications for Linux. Depends that what kind of platform are you working with. So you can create standalone apps also from using MATLAB and whatever applications you developed on that. You don't really need a formal background in signal processing to analyze signals with MATLAB and signal processing tool. Why you don't require a formal background? Because already inbuilt algorithms are available in MATLAB. Whatever are done, all algorithms you can find out in MATLAB. And for each and every functions, there is a proper documentation in MATLAB. Explanation, examples, and algorithms as well for every function. Let's say if I have to do PSK, if I give a if I have to open a doc file for the doc space communications.psk, then I will get the document for that. So for each and every function there is a proper documentation also in MATLAB. Okay, signal analysis workflow. How signal analysis work actually? First of all, you know that we require a time series data. So your time series data can be in files, or you interface other vendor softwares also. So from there also you can access data in MATLAB. Or if you are working on live data, like you have some kind of sensors, from there you are logging time series data. So first of all, for signal analysis we require data, right? Either you are using signal processing or communication, of course we require data from that, right? When you have data, so what we do further, some kind of pre-processing on the data, means designing the filter, removing the things which we require. So data analysis and modulation, you can visualize your data in a different form, like in time series domain, frequency domain. When you are happy with that, further you can design a filter for that to remove the noise from that. Or if you are working on communication, then you require to design a RF end, you require to design a receiver, transmitter, channel after pre-processing of that data. And further you can develop it as an application also. Let's say that you don't want to share your codes, just you want to share your outputs. Create an app, and further after creating app you can create a .exe file for that, or if you want you can create it as a PDF, as a doc file, as a HTML. Depends on you that how are you going to share with your friends and colleagues your algorithms. Further you can deploy your code in hardwares also, like you can deploy in processors, you can deploy in FPGA processors also, FPGA boards. Depends on you. So these things which you see, that they are bi-directional actually here. You can start from here and you can go here and from here. So if you do a single modification at any place, automatically this modification will be done. You don't have to do modification in every stages. Okay. And all these things you can do in MATLAB very easily. Whatever just I told you, signal analysis workflow, we can do in MATLAB very easily, all this stuff. So these are key features of signal processing and DSP. You can generate signals, you can visualize and measurement signals, you can transform signals in different domains. So these examples we are going to see: analog and digital filter design, analysis and implementation you can do, statistical signal measurements and data windowing functions are also available. So this kind of application and analysis you can do with signal processing. And if you want to see a power spectral density of that, if you want to estimate the power spectral density, that kind of things also you can do it. So let's start from the signal generation, that commonly used signal. If you have, then how we can generate that kind of signal. So I'm going to switch here in my MATLAB. So if you don't know about MATLAB, so basically this is a command window of MATLAB. This is a current working directory of a MATLAB. So if you want to execute any file in MATLAB, so it has to be in a current directory. Or if you want to save any file, automatically it will be saved in a current directory if you don't give a full path of that. And here you see that is a workspace. If you define any variable here, let's say 1:10, so as a default it will be saved here. Okay, so we don't have to assign what will be a size of a, just directly you can define arrays here in MATLAB. There are some tabs, so we will discuss during session that what we can do with this. This is an import tab. Let's say if you have data in your file but you don't know what is the function to import data from file, so here you can see these are different file formats which are supported with MATLAB. Okay, and you can select your file, whatever file. Let's say if I am selecting this image file, just I will select this and it will give me a matrix. You see that I have a matrix of that, right? I will finish this and this file will be appeared here in workspace. Okay, just 1 minute. Okay, so this file will be appeared here in the workspace here. And further, if I want to, this is a image file. Simply if I give a image show here, and it will give me a image, whatever image is available there, it will show me an image. That is a blank image, so it is just showing a white. So what we can do, we can just scale that still. So the values are above 255, that's why it shows white. So whatever images are there, you can show like this. Okay, or second one, let's see what is there. See data, that is a main image information. So like this you can import data in MATLAB and you can visualize that output, whatever data you have like this. If you have to plot, then you can plot it also, depends on you that what you are going to do. Okay, now how to generate signals here. So first of all, let me open that live script. So this is a live script actually. So if you are using earlier version, then there is a script file. Still there is a script file. So in a script file you can't visualize the output actually, figures. So when you run that script file, your figures will come in a different figure window. But if you are using live script, you can write your codes, you can write your text, and you can visualize the figures also in the same script file. So here you see that first what I am doing here, this is very important. This just wait a minute. This one, I am creating a sampling frequency, that is a sampling time. Fs is equal to sampling frequency, that is 2000. Just divide with step size, it will become a sampling time. Okay, 0, first value is 0, this will become a sampling time. I mean this will become a step size of time, and last value is 1. So maximum 0 to 1 it will generate, and this 50 is the signal frequency. So first of all, whenever you are going to represent a signal in any software, you have to define the sampling frequency and signal frequency, and further you have to define the sampling time of that. Okay, so now you see I have done this, and further if I have to generate let me remove all outputs from here first of all. Okay, further if I have to generate a square wave, then what I have to do, simply I have to write in MATLAB square 2 pi signal frequency into t, that is the sampling frequency, plot signal. Okay, and further if you have to generate a sawtooth, again 2 pi ft to, this is the sawtooth which we generated from here. This is a simple plot. Okay, if I have to create a sine wave, simple sine 2 pi ft again and plot that. Chirp signal, so you see that in chirp signal 4 input arguments we are giving. So first input arguments is that is your time, sampling time. Second is at f is equal to 0, at t is equal to 0, this is the frequency and this is the final frequency which you see here. So if I run this one, I will get the graphs. You see here, that is a square wave with 50 Hertz, that is a sawtooth wave, and that is a sine wave, and this is a chirp signal. Now let's say I want a spectrogram of that. So simple function is there, spectrogram. I want a spectrogram of a chirp signal, because if I am you see that this is a chirp signal, you can see that frequencies are changing. So what I want to visualize with respect to time how frequency is varying of my signal. This is my concern here, that how frequency is varying with respect to time. Now you see, this is my function, spectrogram function, inbuilt function in MATLAB. I want to use this. So what these things are? This is the window size, this is the non-overlapping. So how will I know that how to get all these properties, what it means? What you can do, whatever function you have, just select this, right click and go in the help. So if I select this and if I right click, if I go in help, here you see that is a window size, non-overlapping, and number of FFT, how many I want. That is a fast Fourier transform, that is a spectrogram, or you may say this is a Fourier. So this is the window and all these properties are there. Now you see that if you want to explanation of that properties, that what that properties are there, just click here, like what is window. So when I click on here, it will redirect to window. Here is the explanation of that window, right? So some others, what is non-overlapping things. So it is, everything is in the documents, it is defined, right? So if I plot the spectrogram of this chirp signal, see what we got here. On x-axis we have time, on y-axis frequency, in the left side, and right side is the power. So you see that this yellow which you see, it's showing that with respect to time how many frequencies are introduced here. So multiple signals are there with different frequencies, you can see in chirp signal, right? So this yellow color is showing you how that first it was a 0, from 0 it started till 150 around somewhere. So that is a spectrogram that you can visualize. If you are using wavelet, you can plot a scaleogram of that also. That is a spectrogram which I am using signal processing toolbox for that. This is the way how you can generate a different kind of signals in MATLAB. Okay, I am switching here again in PPT. Next, acquire and process the real world signals. So for real world signals, lots of hardwares are supported with MATLAB. Let's say that if you want to interface this kind of hardware, CRO which you see here. So for that in MATLAB there is an instrument control toolbox. You can log the data from CRO in MATLAB and you can test your model which you designed in Simulink in MATLAB, and you can display on this CRO again. That is an instrument control toolbox for that. And if you have data acquisition kind of hardwares, like if you are working on national instrument hardware, basically there are lots of DACs available, sensors for right. So you can use data acquisition toolbox. If you want to acquire images, you have an image acquisition toolbox available there for that. And apart from that, depends on toolboxes, like if you have a communication toolbox, you can interface SDR hardware, that is a software defined radio. We will discuss about SDR, that how you can interface. I am not going to interface because it is a live webinar, so whenever I have visit I can show on SDR also, but I will let you know that if you have a SDR and you can interface with that. Okay, one more example I am going to show you. This is about the signal processing. You know that there is a frequent occurrence of sunspots. This is a sun which you see, and we see that there are some kind of sun spots are available there. Frequent occurrence, there is a time interval. Time interval is not a constant. It can be 10 years, it can be 11 years, or it can be 8 years. So every 8 to 10 years there is a occurrence of sunspots. So what we are going to do, we are going to calculate the frequency of that sunspot. So two ways this cycle we can calculate, in time series analysis or using frequency analysis. So two way we can do these things. So I am going to show you both, that how you can find out this cycle using time series or using frequency analysis for that. Okay, so I am switching here in MATLAB again, and let me clear everything from here. I created a favorite command here actually. So if you go in favorite and if you click on new favorite, here you can write something which you want to execute. So it will be appeared here, like I created to clear the command window, close all figures and clear the variables from here. Okay. Okay, let me open this which I am going to show you here. Just sorry, not this one, this sunspots one. So first of all, I am going to load that data and I am going to plot it. So I saved that data as a .mat file here. Okay, this is a MATLAB format. If you want to save something from workspace, whatever variables are here, just save and write the variable name, means file name, that in which file format are you going to save it. So you can save it as a .mat file here. Save, this is my file name, and I will write the variable which I am going to save. So it will be saved as a .mat format. I am going to load this. So you see that I have year, with respect to year I have sunspot data. Okay, so what I am going to do, I am going to plot this. So first of all, I am going to select the x-axis, then y-axis, and if I go here in plot and simply if I click on line plot, I got this plot. So with respect to year, I got a plot here, right? So you see that this spikes which you see, that are sunspots. So we have to calculate the location. If you want to calculate the location, that also we can do, that at what year this sunspot, occurrence of sunspots are, and second, what is the cycle of that. Okay. So first of all, again same thing I am doing which I did just before, loading the data. See here what I am doing here, find peaks. If you give this command, this is a part of a signal processing. It will extract the peaks from your data. Okay, and two outputs you will get, peaks and location, means that is a year in our case, that at what time that peak occurred. Okay, find peaks. These are my data. Minimum peak distance is 6. What it means we defined the distance also based on the x-axis, that after 6 years, because we know that minimum sun occurrence value is 8 years. So we provided here 6. After providing this, whatever occurrence will be there, small spikes will be there, that will be removed actually. Okay, so from here we will get the peaks and the location of that. Further, we are plotting this sunspot data by giving the plot command, x-axis values, y-axis as a blue color, hold on command, and after hold on we are going to plot the peaks as well. So if I run this one, because we can plot peaks now, because we have location as well as we have peaks values also for this. So you see that these are the peaks that shows sunspots. Okay. So that's a very easy to, this is a time series plot, right? So it is very easy to create a sunspot. See what we can do in this case. We have location, right? If I do diff, so it will take the difference from first index minus second index, second will be minus with the third, third will be minus with the fourth. If I give this diff, and this is my locations of all sunspots, after 2 year 13, 21, 30, 39, that is the years which is showing you, right? If I give diff command and location, and also I want an absolute value because I don't want a negative value of that. So if I run this, you see that the first sun occurrence after 11 years, then 8 years, 9 years, you see that 17 years is also available. So I want average year of occurrence of the sunspot. So in this case, just simply I will take the mean value of this answer. It will give me this is the time cycle, that is average time cycle is 10.8696 years, almost 11 years you may say. That's an occurrence of sunspot. Very simple, right? So same thing here I did here. So it will show me a same answer, that is 10.869565. That is the occurrence of sunspot. Now how to do in the frequency domain? So what we are doing here, again, if you are converting in a frequency domain, you have to define the sampling frequency. Okay, that is the number of FFT. Now this is a difference of, that is a sample time, step time. Okay, and this is the sample time. Now you see that we are using FFT shift. FFT shift means whatever zero frequencies are there, that will be relocated the origin. Zero frequencies in that will be located as the origin. Now fast Fourier transform of this time series data, and we are normalizing this here. You see that we are removing the average value from that. Further we are removing that average value also, and this is the number of FFT which we want. Okay, and further to plot this, whatever output we got here, we are converting in a dB, and further we are plotting that. So we are, okay, when I run this, here you see peak is identified. So this is the normalized between 0 to 1. So it is showing the normalized frequency. When you add the mean value, you will get the original frequency. It shows that 8.0918, the value is showing 71.17. That is the occurrence. This is the point, this is the frequency where that occurrence of sunspot is there. So if you have to do frequency domain, just convert in a frequency domain, plot it, and find the peaks by giving the find peaks command, and it's showing the peaks for you. So you see here, one thing is very important here which I want to show you. Here you see that there are multiple peaks. So you have to extract the one peak only from there. So when you use this function find peaks, you have to provide the number of peaks is 1, and sorting as a descent order, means decreasing order. So first it will find out the maximum one. So that's why you have to define the how many number of peaks you want. So first of all it will identify the maximum one. So this is the way how we can do it in a frequency domain. Okay, someone is saying that my video and voice is lagging. So is it for everyone? Just write in a chat box, I want to know that my voice is lagging. Okay, maybe Mr. Prasad, please check your internet connection. Maybe there will be slow internet, that's why maybe you are facing this issue. Okay, this was about the one simple example that how to extract the cycle of anything if I want using the time series data and frequency analysis. Okay. Second, we are going to see signal filtering. That is very important. Here we will see when to choose IR, when to choose FIR, and we are going to compare that also. So in this case, we are going to design filter in a both way using signal processing and DSP system toolbox. Two toolboxes are available there. Okay. So let me show you something here. First of all, what challenges are there to design a filter? First of all, challenges is that I need to find an application for a specific filter. I want a rapid designing kind of things. Okay. Second challenge will be I want to iterate it faster. I want to compare with multiple filters, IR filter, low pass filter, high pass filter, or different kind of raise cosine filter, different kind of filters I want to compare. So I require a fast iterations also, right? Third thing, I want to design a filter for a streaming, means I want to scale the filter coefficients. Means as a default, when you design the filter in MATLAB, that is a floating type, or any software if you are using, that will be a floating type. So how to scale that filters? I want to define the word length of that coefficients of all the parameters of my filter, right? Another challenge is that, okay, I designed the filter, but I want to implement that filter also in any hardware. So how to do this kind of talk? So MATLAB will help you to do this talks, how MATLAB will address all these things. So in MATLAB, already lots of predefined applications for filters are available. So filters are available and applications are available. So it is a very easy to do a rapid designing. So I will show you app also how you can do that. fast iterations, you can visually explore methods and analyze response, frequency response. If you want to visualize, plus let's say that you want a pole in the form of pole 0, how you can visualize that. So this already functions are available. If you are writing a code, then in a single line you can do all these stuff, or you can use apps if you don't want to write code. So both way I will show you. Streamline designing. So in MATLAB we have a fixed point designer. So from floating, why we require to convert our signal properties, whatever parameters are there in fixed type, because if you have to deploy on the FPGA board, so we require to convert from floating to board. So these things are automatic. You don't have to write a code. If you want, you can write, you may not write for that. About design for implementation, so for that we have MATLAB coder to generate C++ code. Simulink coder is there to generate C++ code from Simulink. If you want to deploy an embedded hardware, in MATLAB you have a embedded coder also for that. And if you are working on FPGA boards, and if you want to deploy your filter on FPGA boards, so there is a SDL coder also and SDL verifier for that also. So depends that what kind of hardwares do you have. Okay, low pass filter design in MATLAB. I am going to show you low pass filter. Similar way you can design a high pass filter. So first thing is first, when designing a, just wait a minute, when designing this line, when designing a low pass filter, the first choice you make is whether to design an FIR or IIR filter. So you have to know the difference between them, that what kind of filter are you going to design for that. Okay. Second thing, choosing FIR filter, choose a FIR filters when a linear response is important. See, linear phase response is important for you, then you are going to choose the FIR filter. If amplitude is important, or you may say if linear phase response is not important, then you are going to choose IIR filter for that. Okay, that is an infinite impulse response and this is the finite impulse response. So see again, when linear phase response is important for you, you are going to choose FIR, else you are going to choose IIR filter. Next, if you want to deploy in FPGA boards, FIR filter are also used in many high-speed implementations such as FPGAs or ASICs kind of hardware, because they are suitable for pipelining. So if you want to deploy in FPGA kind of boards, you can go for the FIR. But there is a one issue, we will discuss it later, that what is the issue with IIR and FIR. IIR filters are used in applications such as audio. If you are working on audio signal processing, then go for the IIR. Where phase linearity is not a concern. In audio, there is not a concern about phase linearity, right? Now one thing more, let me explain you. IIR filter take less memory. If you have a FPGA board where memory is less, go for the IIR. FIR filter take high memory. Why? When you design a FIR filter, you will have a numerator coefficients only. But means there is a zeros only. When you are designing IIR filter, there are numerator and denominator both. So that's why IIR take less memory. Means let's say if I am designing a filter with 20 order, filter order is 20 using FIR. Same filter, if you design using IIR, it will take only 2-3 order only. 2-3 order of filter only you have to design it. So choice is yours. Are you going for FIR or IIR? Second thing, we have to ask if you are targeting hardware which has constrained the filter order to a specific number. Let's say if you have a constraint that no, I have this FPGA boards and maximum number of order can be this only. Then in that case you are going for the IIR, right? There you can reduce the filter order. Second scenario, you will have that when you have computed the available computational budgets for your implementation, and this affords you a limited filter order. So that case, if you whatever you calculated and you have budgets for that, then go for high order filters, right? So what I am going to do, what example I am going to show you here, design a filter for a noisy signal where signal frequency is 100 Hz. Further, we are going to introduce noise there as it is written noisy signal here. So, and what objectives is there? We are going to compare with IIR filter and FIR filter for the same noisy signal, and we are going to calculate the cost of both filter also. Let's say if I have to deploy in FPGA, what will be a cost for that both filter? Okay. I am going to switch here in MATLAB again. So I will show you filter designing two ways. One way I am going to use app, and another way by writing command. So first of all, let me show you how to design a filter using app. Okay, I am going to just 1 minute. I am going to clean everything from here. And if you have to use app to design a filter, just click on the app here. That is a part of a signal processing and communication. Okay, so you have to search here that where is the signal processing and communication. Here we have, and here you see we have a one app here, filter designer. Okay, I am going to click this filter designer app. That's the filter designer app. It is very good also for faculties. Also, if you are teaching students, then you can show them if I am adding pole, then what is the magnitude response of that, or if I am removing pole, then what is the magnitude response, poles and zeros, or if you are increasing or decreasing the order number, then what is the response of your filter using this app. So here you see we have lots of options here. Either you are going for the low pass, raise cosine, half pass, low pass, depends on you. High pass filter options are available there, band pass, band stop, IIR or FIR. So also in FIR, IIR there are different methods. In FIR also you can see there are different methods available. Let's say I am going to design a low pass filter FIR, and I am going to use window method. So here you see I am going to design FIR filter, and that will be a low pass filter. In window method, in window I am going to use caser. If you want to see how it looks like caser window, so just click on view and it will show you. That is a time, in time domain, this is the frequency domain, right? Okay, so now I am going to specify the order. Let's say I am going to design a FIR filter and I am going to give a order number, order 20. Okay, okay, and caser, and in caser that is a beta value. So different window methods are there, you can choose any from that. Okay, Gaussian, Hamming, Han, Nuttall, different methods are there. I am going to choose caser. Okay, and now further here you have to provide the sampling frequency and cutoff frequency. Okay, so sampling frequency, let's say it is 1000, and cutoff frequency, let's say it is 20 hertz. So depends on you what is unit of your frequency, hertz, kilohertz, megahertz, depends. Now when I am happy with it, I will click on design the filter. You see my filter is ready here. That is the magnitude response. After designing this filter, here is the option generate a MATLAB code for that. When I click on this, it will generate a MATLAB code for automation purpose. So here you again there are options. Are you going to generate as a function, or are you going to generate with a system objects or data filtering function? I am going to generate as a function. So it is asking me to save, so I am going to save as a IITD1. Okay, it will generate a code for that. You see here, if I had to, whatever constraint I provided, whatever properties I provided, whatever parameter values I provided there, everything is defined here. And same filter, if I have to design by command, I had to use FIR and all these parameters value which I defined, order number, cutoff frequency, sampling frequency, and my filter is ready, right? When I run this, I will get my filter here. Next, if I go here, you see here, if you want to export this filter, just click on the export, and you have an option that how you are going to export as a coefficients only. So as I told, in FIR we will have only numerator coefficients. So when I export as a coefficient, so here if you see here we have only numerators. See, we don't have denominator in this case, right? Now I want to export as a filter, so I can apply on noisy signal. So here is the option that how your system object or object. I'm going to select the object and export this. Okay, so here is my filter ready, HD. See, this is my filter which I designed. So what options are there, what kind of filter is there, what arithmetic is used? It is not fixed point, it is double filter, and numerator coefficients are here also there. Persistent memory is false. Okay, next, what more things we can do with this app? If I want to visualize in a form of pole 0, just I will click here and I will get the pole zeros of that filter. So where are the poles, where are the zeros of that? If I click here, it will give me a group delay of my filter. So it is showing 10. And if I click here, it will show me the phase delay of that filter. If I click here, it will show me the phase response of the filter. If I click here, it will show me the magnitude response of the filter. If I click here, it will show me the filter specifications. And if I click here, this one, and you see that the cost of filter, number of multipliers, how many are required, number of adders, how many requires, number of states, all these parameters values are given here when you are going to design a FPGA box, right? Further, if I go here, sorry, not here, here, this pole 0, okay, if I click here, so I can add or remove poles in this case. Okay, so let's say that I am going to add one pole here and I want to check the effect. So it will take a little time to add it. See, one pole I added here and two poles I added here actually. No, only one is there, and you can see that your filter response and magnitude response and phase response both, right? And if I move this pole somewhere here, and you can see again that this response are changed. That's a very good app that where you can add poles or you can remove poles and you can visualize your filters, what is the response of your filter, right? Okay, after doing this, here is the one option, that is set quantization parameters. What you can do using this tab, you can convert this floating type in a fixed type. You see that as a default it is a floating point, and here is the option fixed point. Why to convert in fixed point? To generate a SDL code. So today we are not going to include this session to generate SDL code, but let me show you how, if you have to generate a SDL code, just click here in target and generate a SDL code. After converting in a fixed point, it will generate a complete SDL code for this filter. Okay, so I am going to close. So this is the way that how we are going to design a filter using app, and how to generate a MATLAB code, how to generate SDL code, and how to export as a filter to apply your noisy signal. Okay, I am going to switch here now. I am going to close this. Okay, here. So first of all, you see what I'm doing here. First of all, I designed the I assigned the sampling frequency, sampling time, and this is my original signal. And further you see here normalize, normal distribution, random noise I am going to add. So first here I created the noise, random, normal distribution noise. Okay, and further I am adding it linearly. So if I run this, you will see the original signal. So you can have your data from your sensors. To show you, just I created a signal. So you see here, this is original, and here you see that is a noisy. Now we are going to design a filter and remove that noise. So to see, one thing is very important, why we convert time domain data in a frequency domain. When you convert your time series data in frequency domain, you will be able to identify what is the frequency of your signal and what is the frequency of noises. And based on that, we design a filter. So same thing we are going to do here. So there is a pwelch command, that is a fast Fourier transforms. So what I am doing here, you can, if you want to know what more properties are here, that is a number of FFT and window size and all these things. I am not going to discuss that. If you want, you can go in help and check that. So you see, this is the inbuilt function for the again Fourier transform using pwelch. In pwelch, I am giving input as a noisy signal, you see, and at last sampling frequency, and remaining what will be number of FFT window and overlapping, I am leaving it as a blank. Further, I will get two output here. First output is power and I have frequency. At what frequency, what is the power? So further I am converting that power in a dB and I am plotting that. Okay, and I am using find peaks also to find out the peak of my signal. Very simple it is. So I am going to run this. So you see here it shows that peak is located at 19.6090 Hertz. That is my signal, because here you see our signal frequency was 100 Hertz around, right? So you see this is a noisy signal, and this spike which you see, that is my original signal in this noise. So what we can do, we can design a filter. To design a filter using signal processing we are talking about. So design filter, this is an inbuilt function. This is a low pass filter, low pass FIR. So low pass FIR, what is the filter order, what is the cutoff frequency of that filter, design method window type, that is Kaiser, and beta value is 3, and sampling rate, that is this 100. So by command you can design like this. Same filter I designed using app also, right? Same filter I designed. So okay, I am going to run this filter. Okay, if you want to visualize the magnitude response of your filter, just give a command fvtool and you will get the magnitude response of your filter. This is the magnitude response of your filter. Okay, next is I am going to apply filter on noisy data. So simple, you have to give a command filter. This is the filter which we designed. So you can select this filter which you designed by command or from the app which we exported. Okay, so I am applying the filter on that, and I am plotting both noisy data and after filter data by giving the hold down command. All data we are not going to plot, it will look very dense because lots of samples are there. So only 100 elements I am going to plot from there. So you see here the blue one which you see, that was a noisy one, and the red one which you see, that is filtered one. So there is not any filter that which can remove the noise perfectly 100%. Okay, but almost it will remove the noise. So you see that this was original. Here if I go original, then noise added. Okay, this is in frequency domain. I got that my signal is somewhere here. I designed the low pass filter. After low pass filter, by giving the filter command, I applied, and blue one is noisy, and this is the filtered signal in this case. Now how to design a digital filter? Sorry, this is also a digital filter. I mean, how to use a DSP system toolbox to design a filter. Okay, one thing here, if you want to extract the coefficients from this filter, the filter which we designed here, this one, SD. So simple command is there, transfer function. That is the kind of transfer function we are extracting, means zeros from that. This is your filter, and if I run this one, I will get the coefficients of the filter. I have this coefficients of this filter. Total coefficients are there 21. Okay. Now to design a filter using DSP is a system kind of things. So always when you use your DSP library, you have to use dsp.fir filter or whatever you want. FIR or IIR, depends on you. So dsp.fir and the coefficients which we extracted from there. This we are providing here as a input. Okay. And further, what do I want here? Just wait a minute. Here I was. This is my filter I designed using DSP system. Next, I want a spectrum of my that filter. So what I am doing, I am creating one system object here. So first of all, any kind of system toolbox, we create a system object, then we execute that. So first I created a DSP filter. It is not executed. It is just a creation of filter. And this to apply to do a spectrum, I just created a one system object as a DSP.system spectrum analyzer. You see here, you don't have to remember this function. Just simply type the DSP and use the tab command. If you want a spectrum, just type the spectrum, and you see the spectrum analyzer will be appeared here. So you don't have to remember that functions. Okay. Okay, we created a spectrum. Now in this case, when if you have a DSP filter, in DSP filter we directly apply my data as an input on this filter, and for the spectrum of this Y step function, and this is my spectrum system, and where we are going to apply that spectrum, the output Y means filtered signal. When I run this, I will get the spectrum of filtered signal. After that we will switch to communication. You see, that is a filtered signal spectrum. Okay. Good, we are going good till now. Okay, now we are going to design. Now you see, let me plot that. It is already plotted, same thing. It will give a same output. Either you are using signal processing filter or DSP filter, same output. See, noisy and filtered, right? And further, what we are going to do, we are going to convert noisy signal in a frequency domain, and we are going to convert filtered signal in a frequency domain, and we are going to compare. So that is very easy. I hope you know the basics of MATLAB. So p-wedge, this is for the filtered signal, and this I am using for the noisy signal, and both I am plotting in a same figure. So p-wedge command is there to convert in a frequency domain. You can use FFT also, like previously we used. It depends on you that what are you going to use. And we are converting by this as a dB, and we are plotting that. That's all. So you see here, two plots are here. The first red one which you see, that was a noisy, and you see that from here noise are removed even in a frequency domain. You see that it is very low. The amplitude, the power is very low of this noisy signal, right? So noise is removed, filtered and noisy signal. Now design the IR filter. So you see one difference here. Here when I designed FIR filter, what was the order? 20, right? Now we are going to design IR filter, and you see that same process, design field, instead of low pass FIR we provided low pass IIR, and filter order is only 2, and same task it will do. Their order was 20. That's why it takes so much memory if you are designing FIR filter. So here order is only 20. Passband frequency 120, that is a cutoff frequency you may say of the signal, and sampling rate, that is 1000, already we defined above. Okay. Fine. And to design, okay, after that, this is using a signal processing. Using DSP, what you will do, you will provide the coefficients and you will design the DSP one, right? So right now let me run this. So it will give you a filter response. First of all, this is the filter response of IIR filter. Okay. Next, what we are going to do, comparing both one by using fvtool, low pass FIR and low pass IIR. That is a response of both filter in a single figure. You can use fvtool and the FIR filter, and this is the IIR filter. Remember, both filters are DSP filter. So you see that this one which you see, that is the IIR filter, and the blue one is FIR. So it allows more till from here to here, right? That is the magnitude response of both. Next is compare the cost. So very simple. Low pass filter we designed. Next, low pass FIR we designed, and low pass IIR we designed. Just simply give the cost, and it will give you a cost for both. So here you see the cost of both filter. See this. First one is FIR. Number of coefficients are 21. In case of IIR, only 3. Number of states 20. In case of IIR, only 2. Multiplication per input symbol, that is 21. In this case, only 3. Additional per input symbol 20. In this case, only 2. So you see that how cost effective this is, right? IIR filter. Now I am going to apply that filter here, and means I am going to apply the IIR filter here. To apply this, very simple, LP IIR, and this is my data. This is IIR filter, and the step command. So it will be executed that spectrum of that also, the spectrum which we created. Okay, so this is this will be a spectrum of that. This is a spectrum using IIR filter of filtered signal. And further, let me compare both. So you see in this case, the red one is IIR filtered using IIR filter, and the blue one is noisy signal. So now you got that what is the difference between IIR and FIR, and when you are going to choose. So when phase response matter, then you can linear phase matter, then you can go for FIR, otherwise you can go for IIR filter. Okay, so here you see they are proper in the phase, and here you see that little difference is there. Meanwhile, if you have a question, you can ask me in a chat box, or I will go for communication right now. My voice is audible? Voice is audible for everyone? Okay, fine, thank you. Here, a recap. We generated a signal, we visualize the signal in a power content of the signal. Also, we design and apply a low pass IIR and FIR filters using apps. Also, you saw that how to design this kind of filters. We compared the cost of filters, right? Some common applications are there. I have this data. If you want, I can share with you. Because of time constraint, I am not going to show this common application, because our main focus is on communication right now. So we are going to see communication right now. So removing the trends from EKG signal, detecting a distorted signal in noise, removing spikes from a signal. So let me show you one example how to remove the spikes. That is a very important. And how you can use live script to remove such kind of noise. Okay, so I am switching here. Just I will show you how to remove the spikes. So we can define a median field filter for that. Okay, so I loaded that voltage. I have a open loop voltage. I loaded that data. Let me clear all output and run it again. Okay, now I am going to run that. I am plotting that data. You see that we have spikes here, right? I want to remove these spikes from this signal. So very simple it is. Just create a one dimension medial filter and apply that, and this is the order of that. Okay, and when I run this, see what I did. I created a median field. We are applying this median filter on that spike signal, and further when I plot this, you see that spikes are removed from that. Other way how we can remove this noise, let me show you. Okay, what I am going to do here, I am going to break it as a section here. Okay, and further one more section I am going to break it here, and here I will show you how you can use pre-processing to remove the noise from the signal. So if I go here in live script, in insert command, there are some task options. Clean missing data, clean outliers, find change points, find local extrema, remove trends, smooth. Let's say if I have to smooth this data, just simply what will I do? I will click this template. A template will be generated here. Means you don't have to write a code for that. So I am going to smooth this data, and I am going to check that by smoothing this will be removed or not. Okay, you see here a template is generated. What is input? That is noisy loop voltage, right? So what I am going to do, just I am going to select that noisy loop voltage. So all these variables are in our workspace here. Okay, now you see here perfectly, you see this line, this blue one, this is after smoothing that, and all these things are removed from there. These spikes are removed, right? Or you can decrease this smoothing factor and you can check again. Perfect. You see the dark blue which you see, that is smooth, and this light blue, that was original one after decreasing this smoothing factor here. So perfectly you can use this. And further what we can do, right click here and convert tasks to editable code. See, code is generated. smooth data, noisy low voltage, we are using moving median method, and smoothing factor, what is there. And you can modify in this course. And this is the my output is where saved data as a smooth data where noise are removed. So if I plot this in workspace here, from here just simply plot, and this smooth data, you see, okay, some spikes are there. So to remove these spikes, what we can do here, we can increase the smoothing factor, right? If you increase this, and further this will be removed, this spikes will be removed. So you can use this, or you can use a median filter for that. Okay, let me switch to PPT right now. So we saw all this, and actually here we saw how to remove the spikes from a signal. Summary, with MATLAB and signal processing toolbox, you can generate signals, visualization and measurement, all these things we saw. Signal transformation like time domain to frequency domain, we saw that. Analog and digital, so I showed you how to design a digital filter. You can design an analog filter also, and how to implement that filter, that also we saw. Statistical signal measurements like peaks, windowing functions, that things also we saw, right? Power spectral density estimation, that's frequency domain, that things also we saw. Now developing and prototyping next generation communication system. So why, first of all, we'll discuss that already we have instruments for communication, but still why we require to enhance all these things. So these standards are already available. WiMAX is available, LTE is available, ISDB is available, DBB, Wi-Fi is available, ADSL is available, but still why required to enhance the communication? When you are studying communication, these things you have need to know that why do we require. First, what is the requirement? You see here new use cases like nowadays the videos are 4K, 8K, 360 degree, virtual reality, which require a high speed internet, right? Remote surgery, that is very precise things. If there is a delay of 1 or 2 seconds, then issue can come. Internet of things, we can't imagine IoT without high speed internet. So when 5th generation of mobile communication is installed in India, that is new radio NR, then you will see lots of applications in India on the IoT, and smart cities also, connected vehicles. So these are the new cases. For that we require to enhance our communication system. And what are the requirements for that? Ultra band, low latency. In 4G the latency is 10 millisecond. In 5G latency is below 1 millisecond. Massive devices connectivity. So in a single area we want to connect massive devices also. Low energy and cost. And how it can be solved? More bands, either we can increase more band or we can increase bandwidth of that. Better spectral efficiency, flexible air interface to remove the fading. Densification means in a single area we require to install the multiple Wi-Fi, that is a kind of densification, or increasing the number of antennas in region. Right now we have sites only, as a, we will discuss about that later, that how 5G work actually. Okay, so road to 5G. See, in 5G we are nothing doing new. Something is new about modulation only in 5G. We are using which are already done to create a 5G, like LTE. We are using LTE and WLAN evolution. We are mixing this to create a new radio technology. How we are mixing? What we will do, in every 200 meter in 5G they will install the Wi-Fi. So when in 200 meter there are around 5-6 Wi-Fis, of course internet connectivity will be enhanced. So we are going to use previous technology LTE or WLAN. We are going to mix with some little modification, and we are going to create a new radio technology for that. Okay. Developing next generation wireless technology. What things we require? We require to design antenna, of course. RF designing is required, of course. Mixed signal hardware we require, so we can differentiate digital and analog both, or if you have to convert from analog to digital or digital to analog, right? These are the requirements. Digital hardware we require, where we can do testing. DSP algorithms require, just we saw some how to remove noise. Software development, we require an app where we can develop that software, right? System architecture also required, the hardware part of that. So total you see that at least 7 skills we require to do all this stuff, right? How this can be sorted out using MATLAB? See, this is a baseband signal, this is a transmitter in, and this is a receiver in, and this is the channel. So here you see, for algorithm, waveforms and measurements, we have some toolboxes in MATLAB. Communication system, phase array, LTE, WLAN. For RF front modeling, we have a RF toolbox, RF block set sub-level. So RF toolbox you can use in MATLAB, and RF block set you can use in Simulink. Antenna array designing, for that we have special two toolboxes, antenna toolbox and phase array system toolbox. For mixed signal, you can use Simulink, DSP, control, and mixed signal block set, which is introduced I think from 1998, mixed signal block sets. Okay. And for antenna kind of designing, communication, phase array, LTE, WLAN, 5G toolbox. So the good thing is that you can interface all these toolboxes with each other. Some I will show you how to interface all these things. So these are the toolboxes you can use to design a complete communication system using MATLAB. Apart from that, if you have to do some kind of testing, let's say that I design my model in the Simulink or MATLAB. I want to test with this kind of hardware and I want to visualize. So there is an instrument control toolbox. Further, you want to do a prototype of testing. So SDR platforms are supported with MATLAB. You see this one, this one. This is the RTL SDR. That is a TV tuner which was coming before. You can purchase in 2 or 3,000. There is one receiving antenna. So you can interface this TV tuner, I mean this RTL SDR with MATLAB, and you can log the FM signal. You can log the airplane data, means track that airplane. So whatever feasible, whatever allowed for you, you can log that data in MATLAB using this RTL SDR. There is ADLM Pluto also. There is a receiving and transmitting antenna both. Okay, so for prototype designing, you can generate C code, SDL code, embedded code, and further for implementation, you can interface processor, FPGA or ASIC kind of hardware if you have. So for that, we have SDL coder and embedded coder available in MATLAB. Okay. So fading channel. So let me discuss that first of all, when you are going to use relay and when you are going to use reshunt. So see, this is your transmitter, this is your receiver. Some signals will go direct, some will be reflected and scattered, and here the some output which you are getting, that is called multi-part fading. So you see, due to this phenomena, the figure which you see, each major part behaves as a discrete fading part. Typically, the fading process is characterized by a Rayleigh distribution for a non-line of sight and reshunt distribution for a line of sight. So when you are going to design a complete communication system, you have to consider AWGN channel also, you have to consider Rayleigh distribution also, and you have to consider reshunt also. Then only you will have a complete communication, because your signal can be a line of sight or it can be a non-line of sight. So non-line of sight, so you are going for a relay, and line of sight you are going for a reshunt. That is very important. So very simple example I am going to show you. First of all, I am going to use a 16 QM constellation. Okay, and that the standard which I am going to use of communication, that is V.29. So what I am going to do, I am going to do a modulation, demodulation, channel, and we are going to calculate SER, SER and BUR in this case. That is a symbols error rate and bait error rate. So what is the bait error rate? Total number of errors divided by total number of samples, right? Total number of bits, sorry. I am switching here, and let me visit here in communication and open that example here. So what will be your first step to create a constellation for that, right? It is a 16 QAM, so we are going to create a constellation for that. This standard is taken from v.29, so you can have your modified standard also. This is a constellation, how we are going to visualize our data, I mean modulate our data, okay? And here you see what I am doing here. Rand I am using to create a random number, means the data which I am going to modulate. So using rand I command, here you can provide the minimum value in a square bracket, and that is the maximum value, and total number of rows 2000 and total number of columns, that is 1. Okay, so this decimal data which I am creating, I am going to modulate this. To modulate this, there is an inbuilt function in MATLAB that's called generate QA modulation. Okay, so here you see what input arguments we are giving. This data, numeric data, and C is the constellation of it. Just nothing you have to do, and your modulation is done in a single line. Okay, now further we are going to define a AWGN channel. So to design a AWGN channel, there is an inbuilt function in MATLAB, or if you have a mathematical equation, you can design that equation also. Better to use the inbuilt function. Why you are going to design again? Use the this, and here this is a modulated data, that will be a complex data, it is there, right? And we are designing this AWGN channel, that is a signal to noise ratio. Okay, and this is a measured, means I don't want other output, just I want this receive signal after that. Okay, now we have a receive signal, this is a final receive signal through the channel which I have. Okay, and here which you see, when I plot this receive signal, I am going to plot. So to plot the receive signal, always use scatter plot. Okay, so you see that this is the constellation it is showing you, that is a standard is v.29. This is the modulation using v.29 16 QA modulation. This is your data. The red one which you see, so the constellation, and this is your receive signal, the blue one which you see, that is a receive data. Okay, now I receive the data. Next I am going to calculate symbol error rate, and I am going to calculate bit error rate. So to do this, we have to demodulate whatever I modulated. To demodulate, I am using this function generate QAM demod. Before it was mod, now it is demod. Okay, let me run this first of all. See, there is a symbolic error. If you want to find out the symbol error, just you have to give a sim error. It will give you a symbols error rate. Okay, so how it works? I just ran this. See how to calculate a symbol error. That is very easy to do. Okay, this is my received signal in the original form, this one, and above which you see. Okay, just wait a minute. Okay, so what we can do here, I want to calculate the symbol error rate. I will do sum, and this is received one, original signal. And what was the original there? Actually I am showing you how this function worked. So original signal was here, right, equal to, wherever this condition will satisfied, I will get value 1, else I will get 0, and I am going to count that one value by giving the sum command. It will tell me how many correctly we received. If I use this sign, it will show me how many are wrong received data. So you see that okay, there is some issue. I think, let me check that. I think there is some spelling mistake. Just wait a minute. Okay, So here I have, this is my data, fine, same thing I used, I guess, right? Okay, this is the output, no? Okay, you see that this showing total 2000, I mean somewhere that error it is showing. And what was the original one? Just wait a minute. This is my data actually, that is the original one. Sorry, I put the wrong name. This is the transmitting original data, and this is the receiving after that demodulation. Okay. That is the data only. Okay, this is the data. So you see here, this is the received after demodulation, and this is the original data which we created using randi, right? So total number of errors are showing 3 divided by numeral, total number of data which we had. It will give you a symbol error rate. Sorry, again spelling mistakes. It will be NUMEL. Sorry. So that is a good in MATLAB. If you have any issue, MATLAB will tell you. So you see that this is a bit error. Sorry, symbol error rate. So you see here, same thing. If you don't want to write by giving a code, you can use sim error command. Same thing it is doing, and you see that same output we got, which I did right now in a command window. Same thing, we have number of errors, and that is a symbol error rate. Now for bit error rate, we can't use the symbols. We have to convert in a binary. So if modulation order is 16, and if you take the log of it to represent a one symbol, 2 to the power 4, so 4 will be there, right? Remember, 4 will be there, 4 bits you require. If modulation index is 16, so what power will be on 2? So you will get the result 60, right? That will be 4. So what I am doing, whatever decimal data I have here, D to BI command I am giving, I am converting it as a binary. Let me run this and show you. Just I am going to run this. And 4 bits I am giving to represent a one symbol. So I provided here 4. Now you see that what is the output? Binary. See? Everywhere there is a binary. Same way it works. Bit error. And this is I am converting. This is, you see that in this case, this one data are 4. I am converting in a single row, single column, and after modulation also I am converting in a single column. Means this is the transmitted one, and this is the received one in a single column, and I am calculating the bit error rate. So 2 outputs I will get. It will number of errors, and another output will be bit error rate in this case. So you see here, number of errors 432 and bit error rate is 0.2160. Just minimize this and let me run this again. Sorry, this one actually I use this one, no? This one I use. So here this is the output here. Number of errors 5 and bit error rate is 6.2500 into 10 to the power minus 4. Same thing by command if you want to do. What will I do? Just I am going to select this. I am switching here. And I will give the sum command. I will provide this original data, I mean before transmitting on channel and before modulation and after demodulation. So wherever this is not equal to, and it will take the sum and it will let me know how many errors. See 5, then the same output we are getting here also as a 5. And now you see here, when we are going to give signal to noise ratio as a 10. Before we gave 20, now we are going to give 10. Now see what will be errors. So in this case you see that when we decrease the SNR value, errors are increased, and symbols error rate is also increased, right? So this is the way how you can calculate symbols error rate and bit error rate. So bit, if there is rated bit, it means you are converting your data as a binary form. To do this, you can use DE to BI. If you use BI to DE, it will convert again in a decimal form. Okay, fine. Next example which I am going to show you, here I am going to create a relay fading channel, modulator and demodulator. Also we are going to create a AWGN channel in that case. Further we are going to calculate the bit error rate. Okay, and with different SNR value we are going to compare the bit error rate in this case. So 2 ways we will compare, using theoretical performance and the result which we get from this modulation and demodulation. Okay, let me run this and clear everything. Here is the mod. So one thing you require to know that if you are using relay, then what properties are available there, what properties you can provide there. Okay, that is important. So this is the way. If you are using communication system, you have to use com dot relay channel. So in this relay will create a relay system. Okay. So if you want to see the help in that, just select this, right? Sorry, just wait a minute. What more properties you can give here, actually that I want to show you. If I go here in help, it will show me the help. Now you see here, if I scroll this below, let me open in a browser first of all. Okay, if I click on this example, this is the relay example. So you see that to create a relay channel, you can provide the sampling frequency, maximum Doppler shift, random stream, fading technique what you are going to use, path gain what you are going to use, multiple properties you can provide in this channel. Okay. Now I am switching here in the code. So first of all, we are creating a system for the relay channel modeling. That's all. So in this case, two properties I am providing just only, that is the sampling rate and maximum Doppler effect, that is the normalized frequency. Now you see, if I run this, just only I want to see that what is here available. Just I am going to copy this and I am switching here. If I run this, and we will get that output. This is my relay channel which I created as system object. So right now we didn't apply on data, just we created that. Okay. Next is, we are going to use in this case differential binary phase shift key. Okay. So we are creating data again using randi command, minimum value, maximum value, and number of rows, and column is 1 in this case. Okay. In this case, we are creating a modulator for DBPSK, and we created a system object for the demodulator also. This two one. Now to modulate that, it is saved as a mod. Just provide the mod and your data. It will give you a modulated data. Okay. After modulation, you have to transmit on the channel, right? So already we created this channel here. In the channel we are providing this modulated data. What will I get the result here? Modulated data after transmitted on the channel. So if I run this, now we have that data. So it will be a complex after transmitting on the channel, right? Okay. Now we have to calculate the bit error rate for that. Okay, or error rate, whatever you say, bit error rate or symbol error rate. So what we are going to do, after doing this, we are creating a AWGN channel by this. We created a system object here, AWGN channel. Why we are creating this? To calculate the error. Okay. Now if I run this only, and if I execute this only after running this, and if I switch here, and if I type it and enter it, you see that signal to noise ratio is there. So if you have to change this signal to noise ratio, so this, use this and dot, and just select what do you want to change from here. Let's say I have to change the signal power equal to, you can give the just value, because this is a system object as a structure, so you can change any parameter from there. Okay. I am switching here. I am going to run this. Now you see, here I defined the different SNR values, 0, then 2, then 4, then 6, then 8 till 20, and I am running the loop till that time. After running this loop, I am calculating bit error rate for different SNR values. So that's why I am running this loop. I am extracting the SNR. When I is equal to 1, then 0 will be here, right? When I is equal to 2, then 2 will be here. Like this we are extracting the SNR, and we are saving this in AWGN channel. Okay. And further, we are applying this on fading channel. Fading channel is what? Which we created after relay. Okay. After applying this, we are demodulating that, and we are calculating the error by using this command, and we are saving it here. theoretically, if you have to calculate the error, just use the bar fitting as an R value. And what kind of modulation are you going to use? Modulation index. Here you have to provide. Okay. So both I am going to compare on semi-log y. Semi-log y means by y-axis will be in the form of log. So automatically it will be converted as a decimal, right? So the blue one which you see, that is a theoretical, and this red one which you see, after modulation, transmitting on the channel, then after demodulation we are getting it. So this is the way how you can create multiple bit error rate on different SNR values. Next, which I am going to tell you, that is very important. Let's say that you want to check bit error rate on different SNR value without writing a single code. So there is a ball tool in MATLAB. Just simply give a command ball tool. Okay. This is a tool which you can use to calculate the bit error rate. Now we have three parts. Theoretical, which you saw just before. Semi-analytic, here you have to provide the transmitting data and receiving data. Okay, what was the transmitting data and what was the receiving data, it will calculate the bit error rate for you. Or you can use Monte Carlo. Three options are available there. Let's say I am going to use theoretical and I am going to use Rishan, and K factor and whatever diversity order is just provided. Modulation type, let's say I am going to use PSK. Okay. Now I am going to plot this. So you see that it shows a plot. This is your signal to noise ratio per bit, and it is showing the bit error rate. So when this signal to noise ratio per bit is increasing and bit error rate is decreasing, right? This is the first way which you can do. Second way, you can, if you have transmitting and receiving data, provide here what is your transmitting and receiving data and click the plot. And here you see, let's say I want to compare with different also. Before I use PSK, and for that I am going to use relay right now. And again I am going to plot. I am going to check the relay. So both are same. See. Now I am going to change, instead of PSK I am going to use DBPSK. And again I am going to plot. So you see the red one is DBPSK. So like this you can compare multiple bit error rate. This is the theoretical. Again I am repeating, this is the theoretical, and here is the option that let's say I don't want first one, which I use relay for that. So you see this is the first one and this is the second one. You can tick or untick also. And you see that we have all this data available here. You can save this data also, export. Whatever you got output, you can export that data. That is the signal to noise ratio per bits and bit error rate. You can export this data also. When I click on this, my data will be appeared here for further analysis. Okay, so you can use this bit error rate also in your case. Okay, next I am going to show you the coverage of antenna. Means how you can do all these things on map. So in this case, we will see how we are going to create a transmitter. Transmitter I am going to choose East of Kailash. Receiver I am going to choose IEEE Delhi. Okay, your institute. And what we are going to do, we are going to measure the distance between East of Kailash to your institute, and we are going to calculate this distance. And second thing, we are going to also, what is the signal strength between East of Kailash to IITD. Then we are going to check that communication link visualization. Means if my signal is going from East of Kailash to IITD or not. Okay. Then we are going to check the coverage area of that also. And after that we are going to see signal to interference plus noise ratio. That is very important. Okay. I am going to switch here. That is very easy to do. For that you require a phase array toolbox and antenna toolbox also. Okay. The way to do this, let me clear everything if anything is open. First of all, I am going to create a transmitting antenna. So to create a transmitting antenna, you have to use TX site. What is the name of it? That is East of Kailash. What is the latitude of East of Kailash and what is the longitude of East of Kailash? That is a transmitting antenna done. Okay, we created a transmitting antenna. In this case, if you don't modify the antenna, as a default it will take isotropic, and you can define the antenna angle, antenna height, system loss, all these properties you can define here. So right now I am going to choose the default. So you see here, this is the east of Kailash. Okay, if I maximize this, so you can see this proper visualization. Just wait a minute. Okay, just wait. Okay, just wait a minute. Let me minimize everything and open this. Okay, fine. Now you can visualize this transmitting antenna is at east of Kailash, right? I am switching here again. Now I am going to create a receiving antenna, that is triple IT, that is a triple IT Delhi, and the latitude is this and longitude is this. Okay, when I run this, here also the receiving antenna on mobile is, that is isotropic as a default, and this is your triple IT Delhi. Okay, now if you have to find out the distance between transmitting and receiving antenna, just give the distance command. It will show you the distance. See here, this is in the meter, divide by 1000. So from east of Kailash, the distance between two antenna from triple IT Delhi and east of Kailash is 2.4173 kilometer. Okay, what is the angle between both sides? So when I run this one, just simply I have to give the command angle tx comma rx. It will give me a angle for that. That is a counterclockwise from east. Just minus this with 90, it will give you a clockwise from north. That is the angle between the both antenna. Okay, next we are going to calculate the receive power to get the signal strength of the transmitter to the at the receiver side. So this is a function to calculate the power, means signal strength of the transmitter to the receiver side. Okay, so signal strength, this is the signal strength of that, and this is the link margin. Link margin means maximum, what is the sensitivity minus this from this sensitivity, this signal strength, you will get the link margin of that. Means what more signal strength is available, you may say in that case. Okay, now communication link. If see here it is written, if a green link source means the signal is going from east of Kailash to triple IT. If it is showing red, means link is not going, signal is not going there. Your receiver end is not receiving the signal. Okay, so let me show this. You see that it's showing green and it proper signal is going from here to here, right? Next, coverage. Just simply you have to give the coverage command and you will get the coverage of the signal. So this is the coverage, this is the total coverage of your signal. Okay. Now next example which I am going to show you here. In this case, my transmitting antenna is triple IT Delhi and my receiving antennas are Noida, Greater Noida, Punjabi Bagh, Aziai Airport, Ghaziabad, Gurugram, Faridabad and Loni Ghaziabad. So what I am going to do, I am going to change my antenna. Before I will use dipole antenna, then further Yagiuda antenna, and I am going to check the coverage of that. Further, first will be in the free space. Second, we will add some conditions also, like rain conditions. Okay. So these things we are the same way you can we can do this task also. So I am going to just open that live script file. So first of all, you see what I am doing here. TX site for receiving, RX site. Name is triple IT Delhi. Latitude of triple IT Delhi. Longitude of triple IT Delhi. Antenna. See here what I am going to use. Here I am using antenna toolbox. Design a antenna, dipole antenna whose frequency is this. Okay. What is the antenna height? What is the transmitter frequency? What is the transmitter power? All these things you can define it. So first of all, let me define the transmitting antenna. Now you see, now here using RX side, that is the receiving side. So receiving side we have 8 places. I created a location, okay, and here this is the sensitivity of all receiving antenna. Sensitivity is minus 90 dB for all receiving antenna, okay. And further RX side, what is the name, latitude, from here we can extract, longitude we can extract from here, antenna, same antenna, dipole antenna, and receiving sensitivity, that is minus 90 we provided here. So this is the way that not only you can design virtually in Simulink, testing is also important. So this is the way how you can test your communication. Okay, now show on the side, I mean on the map. So it will take a little time because here number of receiving antennas are more. Okay, it's not looking better. So let me convert as a street map, right? So let me convert as a strip map. To convert this as a strip map, just viewer the base map, just provide the open strip map. So it will convert as a strip map. Okay. Now let me check. Okay, you see here, this is a, let me increase this. Okay, this is a triple IT daily where I have a source antenna, means that is transmitting antenna. These are the receiving. So you know how you can calculate angle, calculate distance. So that things we are not going to do again. Already we saw before. Okay. Next, I am going to find out the coverage of this. So for coverage, already we told we use the coverage command, and we have a sensitivity of my receiving antenna also, signal strength. Okay. Now I am going to run this. It will show me the coverage of that in that map. You see that Gurgaon is excluded from this coverage, right? Remaining are coming in the coverage. Remaining places are coming in the coverage in this case. Now, by link command, you can find out if there is a green line or red line. So when I run this link, here you see the red one, it is showing that Gurgaon is out of coverage if my transmitting antenna with dipole antenna is installed on the triple ITT Delhi. Okay, this is out of that range. Now let's say add some let's say rain propagation I am going to add. So simply use the coverage command, transmitting antenna. For rain propagation, just provide the rain here. It will use the rain propagation. Before it was a free space. So you see in this case, using the rain propagation, Greater Noida is also excluded from that range. And remainings are still in the range. This is a very good way to analyze the coverage of your communication also. You can design a massive MIMO. Later one example I will show you if I have a time. Okay. Next, we are going to change the antenna. Instead of a dipole, we are going to use Yagi-Uda antenna. Okay, with the same frequency. And we are going to check the coverage. Here, if you give this pattern command, it will show you the pattern of Yagi-Uda antenna. That is a here antenna toolbox is. That is a pattern of that which you see here. Okay. Let me off if any figure is open. And further, same process. TX that antenna. We are replacing. As I told, it is a structure. So now we are providing Yagi-Uda antenna. Okay. And further, what is the antenna angle? Already we defined that, and we are going to plot the coverage and link both. When I run this, so here it will show you a coverage and links also. So you will see that dipole antenna is better than Yagi-Uda antenna using the same frequency antenna if you have. So you see that 4 are excluded. That is Gurugram, and somewhere that will be a low. This is the Loni. That is the IZI. I think it will be there. Okay. So that is Ghaziabad. Ghaziabad is also excluded from there. So you can check your antenna also, which antenna will be better using this application, right? Now to calculate the SINR, here we are providing the SINR value also. It will calculate the SNR for that by providing the signal strength also of that. SNIR is signal to interference plus noise ratio, that is the SINR. Using this you can identify where interference are there, and you see this is the color bar below. If you go below, dark blue is there, then low coverage is there. If you go up, if it is red, then high coverage is there. Based on that, it is showing you the coverage of that. That is a signal to interference plus noise ratio. It is showing you in this case. Fine. Okay, one example I am going to show you on Simulink how to do a live audio modulation. So there you will see that what kind of modulation blocks are available, demodulation blocks are available. Okay. So in this case, what we are going to do, we are going to record the live audio data, pre-emphasize a message signal and modulate it using the FM method. Frequency modulation we are going to use. Then we are going to add wide Gaussian noise to the input signal, that is a AWGN channel. The input signal can be real or complex. In this case, demodulate the complex baseband frequency modulated signal using the conjugate delay method and filter with a de-emphasis filter. Compare the transmitted and received audio signal. These things we are going to do. So I am going to switch here. So my first step is I will show you step by step how you can use it. Okay. So let me clear this everything and open a Simulink. From here I am going to open a blank model. First of all, I need a audio recorder. To get an audio recorder, I will go in library from here. You see that what kind of libraries are available if you are saying first time Simulink. See, these are the blocks available. This is the sources are available in Simulink. These are the sinks available, means where we can see our outputs. These are math operation blocks here. If you have to do addition, subtraction, trigonometry, you can use all these blocks. And after this Simulink library, below are toolboxes which you have installed. So we are going to use communication toolbox, we are going to use DSP toolbox, we are going to use audio toolbox. 3 toolboxes we are going to use for this modulation and demodulation. Okay. So first of all, I require to record data. So for that, I can go in audio toolbox, in sources, and here is the audio reader. I am going to add this. Okay, now we have this. Next, what I require, modulation and demodulation. Let me show you what things are available in communication library. So here you can see there are different kind of channels. MIMO, that is a massive MIMO, multi-input, multi-output antenna system. CISO is also available. AWGN is also available. Some filters are available there. So if you have any query about filters, that after modulation you can use this raised cosine receive filter, right? So this just you have to connect all these blocks there. Okay. DC blocker is also there at the receiving end. Let's say you want to use the DC blocker, whatever DCs are coming you have to block, just you have to add it one by one. That's all. Okay. There are some things available. So first of all, I am going to use channel. So right click, add this block to the model untitled. Okay, now we have a channel also. Further, I will go in modulation. I am going to use analog baseband modulation, and I am going to use FM broadcast modulator baseband. For demodulation, I am going to use this. Okay, now we have all blocks: modulation, demodulation, and channel modeling blocks we have. Next, what I want to do here, I am going to switch to DSP. What more I am going to do here actually? From here, I am going in sync. I want that it will speak also after modulation. That the signal which I am modulating and transmitting on the channel, I am getting perfectly or not. Also, I want to do a spectrum analysis also of it. So I selected this also. Okay. Let's switch to this. So I have all blocks available here. So first of all, I will use this mic to record audio signal. So here there are different options what kind of driver you have. I am going to use WAS API. Okay, and this is the sampling rate, number of channels. If you have 2 channels, then you can provide 2 channels also. So number of channels I am recording as a 1 only. Samples per frame depends on you. You want to improve. I am leaving it as a default in my case. Okay, now next step is FM broadcast modulation. I selected. If I click in this property, so here also you can provide sampling rate, frequency deviation, pre-emphasis, filter time constant, and sampling rate of audio input signal. So same sampling rate which you gave there, you have to provide it here. Okay, fine. Okay, now I am going to use channel, that is the AWGN channel. Here what I am going to do, instead of using this signal to noise ratio per bits, I am going to choose SNR, and I am going to give SNR value 20. Apply. No, this is not a broadcast demodulator. We have to check that for the broadcast demodulator. Just wait a minute. Let me choose from here. That is analog baseband modulation. So here I have FM broadcast demodulator. Okay. Now double click on this. I don't want it will speak directly from here, so I just untick this and I'm going to apply this. Okay, this is my demodulator. I want to see a spectrum also of it. Just I am going to add this here. I want to see a spectrum of input also. Just I am going to connect that. Also I want that it will speak for me. I am going to connect that also. So here again I am going to choose WAS API driver. Now my model is done perfectly. I am going to record for 10 seconds. So as a default here I provided a 10 value. This is the way. It depends on you. If you want to use some kind of filter, just add it in there. That's all which you have to do. I don't have so much time. Otherwise I will be able to show you a complex system also. But I will show you from the example actually. So now I am going to run this. Okay. So now here in the spectrum you can see the spectrum. So still it so here is the for the 10 second you see here. Right, good. Furthermore, what we can do, I want to visualize in the time series domain also. So what I can do, I will go in a signal DSP1 and I will go in sync. I will use this time scope. So what I am going to do here, I am going to add this. Why I am doing in Simulink? That's the easiest way. When you do in the Simulink, you can deploy in, you can generate HDL or embedded code very easily from here. Okay. Also here I am going to add input. Add it. And further I am going to run it again. So I can see in a time domain. That wherever spikes we see which I spoke, and this is a spectrum of that. The blue one which you see, that is the original, and the yellow one which you see, that is after demodulation. And further you see that if you want to find out some peaks value in this case, click here peak finder. Okay. So if I select this, you see that 3 peaks are there to showing. So if you go here, in setting, you can define how many peaks do you want. Let's say I want 6 peaks. So it will show me the 6 peaks here. These are some configurations which you can do. Distort measurement. If I click on distort and harmonics are there, it will measure the number of harmonics also. So it is showing you the harmonics here. Frequency. On x-axis, at this frequency, what harmonics are available there. So harmonics are also there. Lots of tabs are here. you can use that tabs. Because of time constraint I am not able to show. My voice is audible or not? My voice is audible right now? Okay. Okay, I think actually now it is audible. Now? Now? Okay. Just wait a minute. Actually, okay, just wait a minute. Is it audible now? Is it audible? Okay, actually I was using that microphone on Simulink. That's why it was not audible actually. This was the issue. So let me open that model which I designed here. Just to explain you. Because at a time if I have only one microphone, so I can use only one only, that's all. Not this model. This is very complex. Let me show you the simple one. So what I did here, what I was explaining here, see, I use this audio device reader, means to record the data, but if I run it again, then again my voice will be not audible, but because my microphone will be used in the Simulink. This is a FM broadcast modulator. This is the AWGN channel. This is the FM broadcast demodulator. Here you can see the spectrum also. What more I was showing you here, let me open this spectrum first of all. From here you can choose if you have to find, I can't run actually, sorry for that again. So you can, if you select this peak, you can calculate the peaks. If you select this, it will show you the harmonics also, how many harmonics are there. So you can define how many number of harmonics do you want to see. So what I want to say, from the basics you can start, and further you can apply some filters. You can use relay also there. So like this way step by step you can design a complete communication system in this case. So very simple. See, I did it here. Everything, blocks are available, explanations are available. Just you have to connect and play that. That's all which you have to do. Still no audio. Am I audible right now? Am I audible right now? Actually, what is the issue? I am using microphone in the Simulink. That's why it is showing me unaudible. So hope that you got that how you can use Simulink to design a model on for live data. I mean modulation, then designing the channel, demodulation. Further, if you want, you can add some filters there. You can use relay channel also there. Step by step, like you can just add it here and play that. That's all. Let me show you one complex. I am not going to design, just I am going to take from a simple example from here. So if you want to know that in any toolbox how many functions are available, what you can do with that, let's say that I want to know how many functions are available in communication toolbox. Just I will click here, I will go here in function, it will show me how many functions are available in communication toolbox. So let's see, that is a random error, generate the random bit error. Step by step everything is written. If I have to do source coding, I will use this. Previously remember the QPSK, I mean QAM, which I showed you, that as a default it was a gray coding there. Coding is, that was as a default gray coding. Okay, so source coding you can use these functions, and when you click on any function you will get the explanation and examples also. Now if I click on the examples, I will get the examples which are available in Simulink. Lots of examples are available here. You can check this examples if you want. You see that there are lots of examples. This is a passband modulation. If I open this model, you can see what things are here available. Just let me open this model. It will take a little time to open. So you see, just I want to explain that what blocks are available in Simulink and what kind of blocks you can use this. See, it started from the random integer. He used the modulation. This is a raised cosine transmit filter. So these filters are available. Then this is a up converter. Okay, after up converter, this is the AWGN channel, and further he included some non-linear interference also here. And further this is a up converted spectra if you want to visualize. So like this you can design a complete transmitter in. After transmitting on the channel, these blocks are available there. That is again raised cosine receive filter to detect the data, and then demodulation of that. And here these blocks are available for constellation diagram and down converted complex signals. That's a very easy to do all this stuff. So let me switch to PPT, then we will have a question answer for that. Okay. Okay, here. So if you want to use 5G kind of models, so what we require for 5G, that is a key 5G technologies, that is we require massive MIMO, we require a millimeter wave bands, right, new waveforms, modulation schemes, and of course 4G works just on 4 to 6 GB frequency only. 5G will work above 30 GB, and you see that wavelength will be below 1 millimeter, and the transmit to receive the data, it will be below 1 millisecond only. We require a large antenna arrays for that. Design a massive MIMO. So here actually we have a less time. If you have a time, I can show this demo, or just I can explain it here. So same which we visualize on the map, you can create a massive MIMO also, and you can visualize the SNIR, signal to interference plus noise ratio. The process is the same. So in this example, 19 cell sites are there. In each cell site there are 3 blocks, 3 subcell you may say. So you can use do it your own actually this. So in this case I am using reuse 4 technology. So 19 cells, this is a cell that is about, you may say that is a 3G kind of thing. But when you introduce subcells also there, it will become densified. It will be densified. So you can check the coverage, you can check the SINR, depends on you what you are going to check it. Further using LTE system toolbox, which is for the 4th generation of mobile communication in MATLAB, using that you can design FTD, TTD, uplink, downlink, sidelink, transmitter, receiver. These standards are already available in the LTE toolbox. 200 more functions are supported only for the physical layer design. So of course in MATLAB, if you are designing communication, if you are using WLAN, or if you are using 5G, you can design the physical layer only in that case. Okay. 5G channels in 5G toolbox we have 5G channels available. The frequency which it work between 6 gigahertz to 100 hertz right now. New radio, that is a OFDM and WOFDM, that signals also you can generate, that modulation you can do it. Further, you can generate C++ code from that to deploy in a hardware as well. Phase array system toolbox is used to do some kind of analysis, like if you have to track the target, or if you have to do analysis on the Doppler effect, or if you have a mixed signal kind of things, multiple variable signals, so you can use phase array system toolbox for that, for analysis. Okay. WLAN, these are the some standards available, and you can use library of these standards, and you can design your WLAN system also, wireless local area network, using MATLAB. And from this also you can generate C++ code, and WLAN is supported for ATLAB, that is for SDR hardware. Communication is also supported for SDR hardware. You can interface with SDR also in this case. These are about communication examples. So already we saw this. Let me show you about SDR. Just here I am typing SDR. So RTL SDR depends on you that what kind of SDR are you going to use it. Let me do back here. So you see that if I just search the SDR, here it is given that how you are going to set up your SDR. By giving the SDR setup, if I click on this, the process is given how you are going to set up your SDR. Before that, you have to install the support package for SDR. So you have to click here app, go and get hardware support packages, and select the hardware which you are going to interface with MATLAB and Simulink. Okay, so let's say here I want SDR hardware. So just here I will search that see, communication toolbox support package for RTL SDR, communication for the USRP radio. So these are the SDR hardware. That is a ADL. So you can use this. Here you have a transmitting and receiving both, but in RTL SDR you have just a receiving. So it is very cheap. In 2,000-3,000 you can buy RTL SDR from Amazon. Depends that from where you want to buy. Okay. So after configuring this, when you are done with that, if I go in example, lots of examples are given there. See here, if I open any example from here, when you install the support packages, you will get the blocks for that. Just connect that blocks. This is actually a FM broadcast receiver. Whatever FM channels are there, use this to tune that FM channel from here. Sliders are available in library, and you can extract the FM data here. So if you have a baseband file reader, if you have already that, you can choose. If you have a RTL SDR, then you can choose this. But before that, you have to install the support package. If you are using ADLM, so if you are using RTL SDR, you have to install the support package, run this, and you can hear the FM directly from here. That's a very easy to do in this case. So lots of examples are available. Apart from that, if you have any questions, and you can ask me. And if you are beginner MATLAB, let's say if you don't know about MATLAB, there are free courses available for MATLAB, like MATLAB on RAM, machine learning on RAM, deep learning, Simulink, StatFlow. StatFlow is used to design an advanced controller using a graphical way. So these are around each courses are around 2 to 3 hours only. When you complete these free courses, you will get the certificate for that also. So there are some advanced, this kind of certificate you will get. There are advanced courses also, you can, but advanced courses you have to purchase them. So you can do advanced courses also on MathWorks website. So the courses are very good. Let me tell you, I already completed many courses. Courses are very good given. Step by step from scratch you will learn everything. So depends on you, are you going for signal or communication, you can complete that courses also. Okay, if you have any questions, you can ask me. Mr. Hers, you are asking that you are using MATLAB 2014. So if you are a student of IIIT, you can get the latest version from there. There you have a campus-wide license. You can get latest version. So all the features which I showed you, some will work, but some will not work there. Okay, somebody is asking how to do a Mac design. So I will like to tell you, for that there is a WLAN toolbox. Go for the WLAN toolbox. You can do a Mac designing kind of things also. This is a part of a WLAN toolbox. You can design that also. If you have any session in future on WLAN also, then we can show that. But only in 2 hours, whatever possible things were there, I showed you. How to do ML detection, maximum likelihood detection, right, in 4QM. So there these functions are available there. If I go here, simply that is a part of a communication. This is a MLC qualifier is there. The different options are there. There is a MSK detection, that is MSK demodulator also. So you can get that in communication also. So let me tell you one thing more. Just write in a feedback that if you have to, I am not able to show everything actually in 2 hours. So write in a feedback. I will send you a link on your email. Ms. Prachi asked me that how to do a ML detection in 4QM. Their examples are also available. Just write in a feedback. I will send a link regarding that. Okay, Swati is asking any course available for Mac design for VLC. No, right now which I know there is no such kind of course actually on MathWorks, Mac design on VLC. If there is, I will let you know. Please write in a chat and feedback form. Of course, let me share